Hello. Good morning, everyone. Thanks for attending. Yeah, I am Dario. Thanks for the introduction. Today we're gonna have a dive on a service that has been developed by my team 1 year ago, more or less, in which we optimize the transfer of data from Kafka to BigQuery in one of our pipelines. Before, I would like to have some word about my company. That's Adevinta. It's a global brand. Inside it, it comprehends a lot of marketplaces around the world. They mainly operates in the fields of the housing markets, in the automotive, and in the customer-to-customer sell of items. In French, the biggest one is Le Bon Coin. There are a lot of monthly users, around 120 million of active users, and this generates a lot of events in our pipelines that gives us a lot of nice use cases to solve, like the one that I'm going to present shortly. Some spoilers. At the end of the talk, I will show how we saved roughly $40,000 per year with this new application developed, how we were quite happy with the solution. It scaled quite nicely. And also, we released the full code base in the Adevinta Git. I will share at the end of the talk a QR code that you can use it to access. Maybe what you obtained can also be helpful to you. These are the points in which I will go through. First, I will introduce the problem. Then I will have an overview of the design of the service. Then we'll also go through a high-level overview of the CEO framework that has been used to develop the service. And then I'll wrap it up with the results. The presentation will be slightly shorter than the canonical 40 minutes, so I will take more or less 30 minutes for it. So everything started a few years ago. In my company, there was been a migration going on. Everything was on-premise, but there was the need to move in a cloud. So the pipeline was before exposing the data in real time on Kafka, and the data for the analyst, we had the HDFS in combination with Hive. In Google, the solution chosen for let the analyst explore the data was BigQuery. So since we were using the GCP cloud, my team had to build something to move the data in an optimal way. Dataflow is a service provided by Google. It allows to move data quite easily from one source to a destination, also applying some transformation. It's very nice because it's completely managed by Google. So my team didn't have to care about deploying the nodes. It provides out of the box some very useful metrics. There are some auto-scaling functionalities integrated. And so this has been actually implemented and worked for quite some time well. So what could go wrong with this solution? Well, after some time, the traffic ingested in our pipeline started to increase. And mainly, this made us more aware of the cost that this Dataflow job was rising. To give you an idea of the system, this pipeline was being ingested with data used for analytic purposes coming from all around the globe, from most of the marketplaces in Adevinta, roughly 2 billion of events per day, each of them being more or less 5 kilobytes. The main issues that we were having were that the Kafka cluster was composed by more than 200 topics, and Dataflow does not work very well with this many topics, at least in our experience. That's because we tried, to give you an idea, with one Dataflow jobs per topic, but this was not really clean. And also we try with one single Dataflow job to consume and move the data. but this didn't start it up at all. Then we used one Dataflow job per marketplace. The Kafka topics were divided per marketplace, more or less 30 topics each. And the issue was that redeploying the jobs was taking a lot of time because the Dataflow jobs had to be drained and the new one had to be started. And it took 1 hour, more or less. That's not really the best if we want to experiment and do fast deployment. I mean. And also, yeah, the main reason indeed were the high cost. This was what made us more motivated to move away from this solution. So we decided this had to be redefined. This time we moved away by Google technologies and decided to use open source services instead. And also, instead of deploying it to Google, we deployed it through the company data platform that makes that easy for us to deploy the whole service. This is an overview of the application. It's composed by 2 services. The first one, the GCS writer, consumes from Kafka and writes on a staging area. That's Google Cloud Storage, the object storage of Google Cloud. And the second application is the BigQuery writers that reads the data in the staging area and issue the loading job in BigQuery. The whole thing has been branded Kafka BigQuery Express. Yes, it's a little long as a name, but you can find the service with this name in the Alevinta Git. This is an overview of the first service, the GCS writer. It's a Kafka consumer, so it starts consuming from all the topic and all the partitions. And they serialize the data, applies some light transformation, and serialize the data once again before writing them in Google Storage. The transformation that we apply are very lightweight. For example, we enhance the event with the date that will be later used as a partitioning key in BigQuery. Also, the service write the data in Google Cloud, adding some information, some metadata information in the file names. The most important here that I want to highlight is the end offset. So we don't commit offset to Kafka directly, but we manage the offset through the file names. This because if a file is closed and then the application restarts, then and it does not commit the offset to Kafka, what we will do is to create duplicates. In this way, instead, reading the offset directly on the closed file, we are sure that at least we avoid duplicates in this step. A closer look on how the file names look like. We have several information. We have the topics from which the events have been extracted, the table from which in which this will be loaded, the Kafka partition, always from the topic from which this has been consumed. Then we have the schema ID that will be used to serialize and deserialize the event, calling the schema registry. And then, yeah, we have 2 files. The first one is the .avro that contains actually the data. And then we have also a .don file. This is empty. It's just something that we save in Google to be sure that the counterpart .avro has been completely written and closed. This also contains the end offset. So we have both the first offset and the end offset for every file. These files are written for 5 minutes. This is to make sure that we don't have many small files in GCS. This is instead the second application, the BigQuery writer. What it does is to read the Google Cloud Storage staging area, and then it constructs the loading jobs to BigQuery. We try to do it in an efficient way. This means that all the files that can be loaded together are loaded together in a single loading jobs. The upper limit for BigQuery is around 10,000 files for a single loading jobs. And also we do this every 15 minutes. That's the minimum, so it means that the data in BigQuery are at least 15 minutes old. This is not an issue though, because these data are used for analytical purposes. And doing this more often faced us with issues in the quotas, because there is a limit on the number of daily loading jobs that can be issued to BigQuery. If we had one loading job every 5 minutes, we would have exceeded these quotas. Then, after the file are loaded, the BigQuery writer also cleans up the staging area. But doing this, we always make sure to leave the most recent done file for every topic and every partition. This is because at startup, the file will be used indeed to start consuming from that particular offset for that topic and for that partition. This file can also be used if we, for example, want to do some maintenance operation and we want for one topic and one partition to start reading for one given offset. We can manually add one file in GCS and then the application will start reading from there. Okay. Then some word regarding the staging area. We implemented this solution using this staging area because we read some documentation regarding BigQuery, and one of the preferred way to load data in batch was indeed using a staging area in Google Cloud Storage. Once the data are there, Google will take care of loading the data in an efficient way. Also, if one loading job fails, we don't need to read the data once again. We still have them there. And yeah, it's also free as far as the data in the staging area are in the same region as the BigQuery dataset. Regarding the schema, we use Avro everywhere. In Kafka, we have Avro. In Google Cloud Storage, we have Avro. And in BigQuery, we load directly the Avro data. The schema is auto-detected by BigQuery. And this helps us define the schema of the table without any additional task by our side. And this is good as far as all the eventual evolution of the schema are back compatible. That's our case. We evolve the schema quite often, but always in a back compatible way. And this means that we don't need to do any maintenance operation on BigQuery when this happens. Yep. Some small words also on how we deployed the thing. We use the Adevinta Common Platform. That's just a Kubernetes cluster with some quality of life improvements. And also the CI/CD is handled with Git Action in combination with Argo CD. And we are quite happy with that also because it allows us for observability and how the configuration changes. It gives us some information regarding how the nodes behave after every deployment. So yeah, this was how we managed the deployment instead of relying on Google. Great. Now I would like to have a little overview on CEO. The code of the service is completely used in CEO. That is a library Scala for asynchronous concurrent programming. Most of you know about it. But I will go through the main advantages of using it. For example, that you can use it to wrap any JVM technology. The overheads that it adds to the Scala runtime is quite minimal. You can exploit with CEO the full power of the Scala compiler. it provides very nice resources for avoiding leaking resources. And also, everything in CO runs with fiber that are how it allows for a high degree of concurrency. And also, I will describe briefly the Z-stream, that how application, since our application heavily relies on them, everything is a stream in both the services before. So this is a simple example of a trait matrix that implements, it defines a function, Prometheus report. The return type of this method is a CO. We can see the CO type signature is composed by 3 classes. The first is the environment, that is what the function needs to execute. In this case, any doesn't need any dependency. Then we have the error type that affect my throw, my fail width, I mean. It can be a custom exception, it can be a generic throwable, it can be nothing if it is a par function. And then in the end, we have the actual return type of the effect. This, how can we wrap a service with a CO? It's similar to how we operate in object-oriented programming. In the end, we are just programming two interfaces. So in the classic pattern to use a service with CO, use 3 main building blocks. The first is just the trait that defines the functionality. The second is the implementation, here called metric live. Live is just a suffix that we add in CO as a convention. In this case, we also have a member in metric live, that's metric dependency. This will be later passed by to when we instantiate this class. We implement also the Prometheus report function. All the logic is wrapped around a CO.attempt that will make the logic be executed over a fiber, and also will make the result being a CO. The third building block of constructing a CO service is a companion object for the implementation. This defines a layer. The layer can be seen as a builder pattern that defines how to instantiate the class. It can also be very useful because it can also be used to define how to clean up the resources of the class. Then what we do here is that we call the CO.service method to get the metric dependency implementation. So the caller where this layer will be called, also the implementation of metric dependency will be passed, and we will obtain that here automatically. And in the end, we will construct actually the metric live implementation, passing the dependencies. With this layer, we will obtain a data layer. That's how CO will, how you provide an implementation to CO. I will show this soon. Okay, this is the main class. This is the actual main class of the service without any further simplification. So it's quite minimal. What we do is first log the config, and then after that we start up a simple HTTP server that exposes the basic health check endpoints, the metrics endpoint, and concurrently we also define the message processor with the main logic that's defined inside the run method. Then we still need something here. It's not finished. Yeah, we need to inject there all the implementations, and you do it like this. So you provide all the layers previously defined. What you will do is to automatically resolve all the dependencies. If in a layer you need different implementation, if these are passed in the provide method, this will be actually obtained there. And also it will raise an error if a dependency is passed multiple times or it's missing. Yeah, regarding the fiber that are used to obtain the high degree of concurrency, this can be seen as an implementation of green threading, but also they can be thought as analog of Java threads that perform much better. One thing is that with just a few JVM threads, up to tens of thousands of fibers can run concurrently. That this is quite nice indeed. Also, fibers are very lightweight to create, and also yielding the execution from one fiber to another is a super fast operation. We remove almost all the preemptive scheduling overhead that we usually have with Java threads. Also, if Java threads are synchronous, fibers are by definition asynchronous. And also they are typed and composable. This means always with in relation to Java threads, there if you want to start a thread and run it, you will have to define a run method that returns void. So you can not really act on the return type of this run method. Instead, in CO, we saw that every CO has a return type. And so you can actually take the return type of a fiber and act on it in some way. Even if in my experience, I have to say this does not happen often. If I had to, I mean, in general, I never fork a fiber directly. I work on collection using CO utilities to work parallelly and concurrently on these collections. And CO will take care underneath to fork the fibers and wait for them. Some word on ZStream. Well, this is how, it's just an example in which, taken by the code, in which we list the files in GCS and transform them in a stream. Everything starts with the storage Google API. We list all the files present in the bucket in the staging area, and we create a stream with that. Then the ZStream from JavaStream allows us to convert the Java stream into a ZStream. What we do here is also to wrap the logic into a CO.attempt blocking. This is very useful because it allows us to execute this logic. That's an IO logic into a separate thread pool that is blocking. In this way, the other fibers running in the non-blocking thread pool are not disrupted at all by this. And yeah, in the end, we are just unwrapping the ZStream itself, because otherwise we would have a CO and the ZStream would be in the result. With the unwrap, we simply return directly the stream. And the caller of this function will be free to map over the stream and do whatever they want. Okay, so I wrap everything up. What we obtained in the end. Yeah, consistent cost reduction is the main advantage of the whole thingy. We saved roughly $40,000 per year. We scaled down in the Dataflow job. There were at most 13 nodes with 2 CPUs and 16 GB of RAM. That, by the way, by the automatic auto-scaling capabilities of Dataflow, yes, it scaled up automatically, but after that it didn't really scale it down, at least in our experience. So it was slightly problematic on this sense. We moved to our application that only runs in 4 nodes, each one of them with 3 CPUs and 16 GB of RAM. Also, we improved the control that we had over the system. Now we had the occasion to, before we were relying maybe too much on the custom monitoring that Google provide, we took the occasion to improve it. We added a lot of better dashboards. We also manage the nodes by ourselves, so we have more control how the nodes are deployed. But most importantly, I would say that we reduced the deployment time drastically, because before we had to drain the Dataflow jobs and wait to start new ones. Now instead, with a few minutes, we can redeploy the whole service. Yeah, and in the end, we obtain a working application. It has been 1 year working quite fine. Hopefully, it will not fail tonight, and we are quite happy with that. Yes, I finished the slide earlier. Thank you a lot for your attention. You can find my LinkedIn, and you can also find the code. Please let me know if you are interested in it. You can find me. You can just send me a message.
Hello. Did you explore other solutions like Kafka Connect, like to push the data to Google Cloud Storage, or any other solution of the market?
Yeah, the fact is that we had a very strong engineer that know a lot about SEO. We had some internal push. And also, we had a similar application that was already loading the data on Google Cloud Storage. So we took inspiration from it. And since one of the preferred way to load data in BigQuery was to have the data on Google Cloud Storage, we went with this solution. We didn't explore it too deep, Kafka Connect and other alternatives.
Thank you.
Any other question? Okay, thank you very much.